Hello, welcome to another module in this massive open online course. So, we are looking at a classification of signals. Let us continue this discussion. Let us look at yet another class of signals, which are the exponential, the real exponential signals. Okay. So, what we want to look at is another class of frequently occurring signals, which are the real exponential signals. Okay. And in real exponential signals, well, simply referred to, and these are simply referred to as exponential signals. Similar to what we have, if it's complex, then it's referred to as a complex exponential. If it's a real exponential, it is simply referred to as an exponential signal, which is of the form x of t equals e raised to the power of sigma t, and if sigma is greater than or equal to 0, it is increasing. At t equal to 0, it is 1. At t equal to 0, it is 1, and as t tends to minus infinity, e to the power of t tends to 0. All right. So, it is always positive. So, e to the power of sigma t for any t is always greater than or equal to 0. Okay. Always greater than, always, this is in fact a positive signal. Okay. Okay, this is in fact a positive signal, e to the power of sigma t for sigma greater than or equal to 0. This is increasing. Okay. At t equal to infinity, it tends to infinity. At t equal to minus infinity, it tends to 0. And similarly, when sigma is less than 0, it is a decreasing signal. All right. So, when sigma is less than 0, it is a decreasing signal. Okay. So, once again, at t equal to 0, it is 1. So, let me just draw it. Correct. It's decreasing. At 0, it is 1, e to the power of sigma t for t less than equal to 0, for sigma less than equal to 0, or for sigma less than equal to 0, this is a decreasing signal. Okay. This is a decreasing function, and at t equal to, as t tends to infinity, e to the power of t tends to, e to the power of sigma t tends to 0. Similarly, here also at t tends to minus infinity, e to the power of sigma t, e to the power of t, e to the power of sigma t tends to 0, but this is only for sigma greater than 0. For sigma equal to 0, obviously e to the power of sigma t is going to simply be e to the power of 0, which is 1. That is for the case when sigma is 0, e to the power of sigma t is unity. Okay. So, for sigma greater than 0, it tends to 0 as t tends to minus infinity. For sigma less than 0, it tends to 0 as t tends to plus infinity. Okay. All right. And the last class of signals which are also very important and one of the most fundamental classes of signals is the sinusoidal signal. Simply a real sinusoidal signal, we have already seen a complex sinusoid. So, it is a sinusoidal signal or a real sinusoid, which is frequently referred to as simply as a sinusoidal signal, and this is x of t equals a cosine omega naught t plus theta. A is the amplitude of the sinusoid, all right. Omega naught is the angular frequency or radian frequency, and theta is the phase or the phase offset. Okay, theta equals, this is the phase of the sinusoid, and the frequency f naught, as we already seen, is given as omega naught divided by 2 pi, and omega naught is the f naught is the fundamental frequency of this, the quantity f naught, right, correct. We have also seen that it can be represented as a cosine 2 pi f naught t plus theta. F naught is the frequency, or it is a fundamental frequency. Okay. This is a periodic signal, of course. The sinusoid, it's a periodic signal, all right. I think everyone should be familiar to that, one of the most classic examples of a periodic signal. So, this is a periodic signal and f naught is its fundamental frequency. Now, let us look at some basic discrete time signals, which again occur frequently in the analysis of systems. Some basic discrete time signals. Again, the unit impulse un equals 1 for n greater than or equal to 0, 0 for n less than 0. This is termed as the unit function, okay, the unit step function. Discrete unit okay, this is the step function, the unit step function, all right, which is basically, if it's a discrete time signal, okay, which means it is defined only at discrete time instants. Therefore, it is for n greater than or equal to 0, it is 1, and otherwise it is 0. So, this is 0 for n less than or equal to 0. So, greater than n less than 0, it is 0. For n greater than or equal to 0, it is equal to 1. Okay. So, this is your unit step function. Okay. And similarly, we have the unit impulse function, all right, delta n, which is 1 if n equal to 0 and 0 otherwise. So, we have the unit impulse function similar to the impulse function for the continuous time. We have the unit impulse function or the unit impulse signal, which is basically the following thing. It is 1 at n equal to 0, this is n Okay. So, 1 at all other values of n it is 0. Okay. So, this unit impulse function which is represented as delta n equals 1 for n equal to 0, 0 for n not equal to 0. Okay. So, this is 1 for n equal to 0, 0 for n not equal to 0. This is the unit impulse function. Okay. All right. And as can be seen, this has also some interesting properties. For instance, if you sum from minus infinity to infinity, delta n, this is equal to 1, and further we can also have the shifting property for this unit impulse function, similar to what we had for the continuous time scenario, that is k equal to minus infinity to infinity x of k delta n minus k equals x of n. This is basically the shifting property of the unit impulse function, or a shifting property for discrete time signals. The shifting property for discrete time signals. Also, you can see that delta n equals un minus 1. Un is of course the unit step function, the discrete time unit step signal, and un minus 1 is the unit step signal shifted by 1. All right. So, un minus 1 gives us the discrete time, the discrete time impulse or the unit impulse function. Okay. And similarly, un also alternately un can be written as summation, you can verify this, k equals minus infinity to n, k equal to minus infinity to n delta of k. Okay. So, delta of k, if summation k equal to minus infinity to n is the unit function. If n is greater than or equal to 0, obviously this is going to be equal to 1, and if n is less than 0, then summation k equal to minus infinity to n of delta k will be 0. Okay. So, this is again another representation of the unit step function. Okay. And finally, we have the complex exponential discrete time signal. We have a for discrete time a discrete time complex exponential, which is defined as follows. X of n is e raised to j omega naught n, where omega naught is again the frequency which is equal to cosine omega naught n plus j sine omega naught n. And of course, now this signal, the periodicity of this signal, let us look at what is the periodicity of this signal. In particular, is it periodic? We would like to ask the question is this discrete time exponential, complex exponential, periodic, and the answer is slightly complicated. Although we have seen that the continuous time complex exponential is always periodic, and the frequency is the fundamental period is given as 1 over f naught, correct, or 2 pi over omega. The discrete time complex exponential is slightly tricky. The reason being as follows. So, let us look at this e to the power of j 2 pi f naught n, where f naught equals 2 pi omega naught, or f naught equals omega naught divided by 2 pi. This is equal to e to the power of j 2 pi f naught into n plus n, where n is the period, equal to e to the power of j 2 pi f naught n times e to the power of j 2 pi f naught n. Now, this is periodic only if this quantity equals 1, that is e to the power of j 2 pi f naught n equals 1. So, this is periodic if this quantity equal to 1, which means f naught n must be equal to an integer. F naught n must be equal to integer, in which case this will be e to the power of j 2 pi k, which is equal to unity. So, f naught n must be equal to any integer k, which means f naught equals k over n. So, it must be a rational number. Okay. So, the condition for periodicity of the discrete time impulse is that f naught must be equal to k over n, which is a rational number. Therefore, e to the power of j omega naught n is periodic only if f naught, that is omega naught by 2 pi, equals some k over n or some m over n. Okay. Some m over n, that is, this has to be a rational number. Okay. So, that is an interesting aspect of the discrete time complex exponential. While the complex exponential for the continuous time is always periodic, the discrete time complex exponential is periodic only if its frequency is a rational number. Its frequency is a rational number, or the angular frequency omega naught divided by 2 pi is a rational number. Okay. So, this basically completes our characterization of classification of signals, where we have looked at a broad set of signals which frequently arise from practice. Of course, there are several other signals, because it is not possible to characterize the entire set of signals. However, we have managed to classify a fairly large set of frequently occurring signals, or frequently or very frequently occurring signals, in practice. The properties of these signals are important to understand, because these arise frequently in practice, and these are important to understand the principles of signals and principles of analysis of signals and systems. All right. So, we will stop this module here and look at other aspects in the subsequent modules. Thank you very much.